Okay guys, this is part 5 of the linear system theory, and we are continuing the solution of non-homogeneous state space equations. And in the previous class we established that if you have remember from the differential equation x dot is equal to ax, together we got and C and plus bu, non-homogeneous differential equation. We got together derive this solution. X of t is initial condition of x, e plus at plus e plus at, integration from 0 to t, and we change the variable for the integration, a tau and bu d tau. And this was solution of that we derived in the previous class, if you remember this, right? So now the situation is this, that what happens for vector matrix. So we have the same solution. So here in the vector matrix or state space equations, so we have state space vector x dot is equal to matrix A, here was a scalar, in x plus bu. So this is vector, this is m by n matrix, this is m by 1, this is a scalar because CISO system here, and this is m by 1, that's right, and here is m by 1, that's right. So we get exactly the same solution, except that we have x is a vector of state variables. So x of t, I'm copying from here, is the state vector at the initial value at time 0, x of this, EAT, exponential matrix, the matrix exponential that we know, that we calculate from previous classes. So EAT, matrix exponential, is Laplace inverse of, if you remember, SI minus matrix A inverse. See that we calculated, remember? So, and now plus integration from 0 to t, E A matrix, t minus tau. Look at here, guys. If you take this inside, gonna be E A t minus tau. That's right. So here we have a matrix E A t minus tau, and the B, instead of B scalar, you have the vector. That's right. B u tau. That's right, and d tau. So this is the general solution for, and this is solution for the state space equation, which is this. That's right. So we got that. So, and we know that, again, I'm just writing here, we know that from here, e power of a t minus tau is e a t e minus a tau. That's right. We know from the matrix exponential properties. So let us but derive this. So the immediate approach that we can employ is the Laplace. Oops, what happened? Hold on, guys. Okay, guys, it is a Laplace approach. Laplace approach, that's right. So what is that? We have this state space LTI system, AX plus BU, that's right. So if I apply the Laplace transform on the both sides, and you know from the undergraduate control, and what you get is this is s x of s, because this is vector, minus state variables at time 0, initial conditions. So here is a x of s, right, plus b u of s, because we know from undergraduate control, for refreshing your mind, that d over dt of x, when you apply Laplace transform, gonna be s x of s minus x at time 0. But here you are dealing with the vectors, right? So now I'm gonna move this to this side and this to that side. So we get s x of s minus a x of s is equal to what? Is equal to x at time 0 plus b u of s. That's right. So now you can have this x of s. S, you cannot leave it like s because you're dealing with the matrix. So I, instead of 1, you have to put I, identity matrix, minus a is equal to x at time 0 plus b, vector b, u of tau. Here that we have seesaw system, single input, single output, so you have a vector. U is the scalar. That's right. So now, because this is vector, you cannot divide the both sides. You have to do what? Yes, you have to multiply the both sides by the inverse. That's right. You have to multiply by si minus a inverse. So if you do that, let me go to the next page. So if you do that, x of s gonna be, because see, inverse by this gonna be 1, or I mean identity matrix. So now I'm multiplying 1 by 1. So what you get is x at this si minus a inverse, right, plus si minus a inverse b u of s, right? But this is s frequency domain. That's right. You want to find in the time domain solution of a state space LTI system. So what you're gonna have is this. You have to what, from undergraduate control, if you want to back to time domain, yes, Laplace inverse. That's right. So if you do that, you get x, this is vector again, x of t is what? X at time 0 at initial conditions, si minus a inverse, and let me rewrite it because I need space. X at time 0, so Laplace inverse plus Laplace inverse of si minus a inverse b u of s. That's right. Right. Yes. And I'm sorry, you have to put this like here to all of them. I'm taking this out because this is just initial conditions. That's right. So first of all, based on whatever we have here, we know that this is equal to matrix exponential, right? So let me do that. So this is equal to initial condition of state vector variables. This is EAT. We got that. Look at here. We got the solution like this. Now, here you have to know about the convolutional and the Laplace of the convolutional. So if you remember from the graduate, Laplace of f g, that's right, it is integration from 0 to t f t minus tau g tau d tau, and this is Laplace of convolutional. It is f of s g of s, right? Understand what I'm talking about? So exactly we have here, you see that this is S and this is S, U of S and this is S. That's right. So that's why the Laplace of this, the Laplace of S I minus A inverse, and this suppose this is your F and this is your G. That's right. So the ends to, let me change the color, plus this integration from 0 to t. That's right. So because this is your F Laplace inverse, so this is EAT, so let me EA, but t minus tau, that's right, and B and U of tau, your G, and d tau, and you got the solution, guys. This is the solution, right, as we had previously, right, So, and so here we use the, again, convolution integral. This is on the graduate control that we are teaching at ME 530, that's right, or ME 330. So we got the solution. This is important that we know about this, that's right. So, and now we have everything. So now let us go for an example. I have an example here. So example is this, guys. Hopefully I have it here. Yep. So okay. So example is this. Example. Obtain time response of this. You have a second order system, so you have two state variables. This is your A matrix 1, 2, 0, 1, 1, 2, 0, 1, and the x1 and the x2, plus this is your B, that's right, BU, seesaw system, that's right. Here we go. This is your A matrix and this is your B matrix, and your X is what? X1 and X2. You have second order system, that's right. We want to find that, so the time solution of this, that's right. Okay, hold on, guys. This is freezing. Okay. So okay. So now let me find that. So how to find that? Okay. This is problem. Okay. So find that for unit step function as input, means your U of t is unit step function under graduate control, that's right. And assuming x1 at time 0, initial condition is 0, and x2 at time 0 is 1. So we want to find the solution of that. So we had x of t based on whatever we derived is EAT and x at time 0 plus 0 to t EA t minus tau b u tau and d tau. This is that we're going to use this, right? So first we have to find EAT. EAT is what? Laplace inverse of, as I taught you, SI minus A inverse. That's right. So SI minus A gonna be what? Your A is, let me write here. Oh. Your A is 1, 2, 0, 1. So SI minus A gonna be S minus 1 minus 2 0 S minus 1. That's right. This is this. So inverse of that SI minus A inverse gonna be adjacent of this, which gonna be S minus 1, and changing the non-diagonal elements. That's right. Divided by determinant of this matrix, which gonna be this minus 1 square, and this is 0. This multiplied this multiplied by this. That's right. So what you get finally is 1 over S minus 1, 2 over S minus 1 square. That's right. And 0, 1 over S minus 1. Here we go. That's right. So what we're going to do, we have to find Laplace inverse of 1 over S minus 1, 2 over S minus 1 square, 0, 1 over S minus 1. That's right. And you remember from undergraduate control that Laplace of E plus minus AT, it is minus is S minus plus A. So if it is plus, okay, that's right. Yeah, it is plus, minus. This is minus, this is gonna be plus. So here is minus, so this is gonna be plus. So Laplace inverse of this, based on whatever I wrote here, gonna be how much? And the same for this. So it's gonna be how much? Gonna be E, and your A is 1, ET. That's right. And now we have to find the Laplace inverse of this. That's right. So first of all, you have to 2 over S minus 1 square, you have to do part by part. So you have to A in S minus 1 plus B in S minus 1 square. Okay, hold on, I want to just, there's a bug here. So if you do the calculations, I'm just skipping because it's time consuming and this is trivial mathematics. You get that A is 0 and the B gonna be 2. That's right, B gonna be 2. Just do it at home and you can figure out. That's right. So now Laplace inverse of 2 over S minus 1 to the power of 2 or square, it is how much from undergraduate control? It's very easy, guys. Remember that if we had, I'm just refreshing your mind, Laplace of if f of t is f of s from undergraduate control, so Laplace of E, that's right, E minus AT f of t gonna be f of s plus a. Remember, if you forgot, you can refresh your mind. That's right. So on the other hand, your A here is what? Your A is your A is your A is your A is 1. That's right, huh? Your A is 1, right? So so now you have to judge. So which function gives you 1 over s squared? This function gives you such a Laplace transform. T, remember? Ramp function. This was a ramp, remember? Ramp function. Understand? T. So Laplace inverse of this simply gonna be 2, that's right, and gonna be T E T. That's right, Laplace inverse of this gonna be time exponential of t. That's right. Well, I think this is if I'm not wrong, this is plus. Hold on, I'll double check. I'm getting over. No, this was minus. I was right. That's right. This is minus. Because your A here is minus 1, so minus 1 is going to be plus. So we found that. So matrix exponential going to be based on whatever we found from here. E exponential of t, 2t exponential of t, 0 e exponential of t. Bingo, right? Or why we are finding this? Because this is part of our solution to the state space equations. See this? Understand? So now we can expand this. How? We say x of t gonna be, okay, so EAT, so ET, 2t, ET, 0 ET in, look at here guys, x naught. Your x naught, sorry, x0 means at time 0, based on the given information of the problem, is 0 and 1. So 0 and 1. So in 0 and 1, that's right, right? So EAT x naught, okay? So plus integration from 0 to t. Now, once you found matrix exponential, you can change the variables. So gonna be, you look at here, so EAT, just replace t with t minus t. See, it's gonna be exponential t minus tau 2 t minus tau e t minus tau 0 e t minus tau, that's right, in b. Your b is how much? Look at here, your b is 0 and 1, right? In b, that's right, 0 and 1, and your u is step function. So look at here guys, this is under graduate control. If this is a step function, u of s is 1. Remember, Laplace of this step function is 1. So in 1 dt, right? Right? So now if you do multiplication, so what you get is this. E look at here, so this is 2 by 2 and this is 2 by 1, gonna be 2 by 1. In multiplied by this multiplied by this, you're gonna 2t et, right? This multiplied this multiplied by this et, right? Plus from 0 to t. Now for this part, this multiplied by this multiplied by this, so it's gonna be 2t minus tau e t minus tau, and this multiplied by this minus e t minus tau in dt, right? Clear? So, and if you do this integration, especially for this part by part, I'm skipping that because it's time consuming, you can do at home. So the solution gonna be finally 2t et, and the integration of this finally gonna be e exponential of t plus 1, and minus 3t minus 1, and here's gonna et minus 1, and you can sum together. Hold on a second, I'll double check everything. I'm sorry guys, I have to revise this part because I double checked. So this is gonna be 2et t minus 1 and plus 2, okay, 3 plus 2, and here we are, and this is right. So if you add them, you get the general solution for this problem. Okay, so now you can have a practice at home. Find solutions of the following state space equations. X dot 1 is equal to x dot 2. X dot 1, x dot 2 is equal to A matrix is 4, is 5, minus 2 and 3, and x1 and x2, plus seesaw system 2, 0, and u. And the other third order system, you have 3 state variables, x dot 1, x dot 2, x dot 3. That's right. It is 2, 0, 1, 0, 3, 2, 1, 1, minus 1, and in x1, x2, and x3, right? Plus, again, this is seesaw system, so we have only one. And the initial conditions for this x at 0, assume this is 0 and 2, and the initial conditions for this gonna be 1, minus 2, and 2. Find the solution for this. Okay, so after knowing this, but you have to know, in addition to this approach, in addition to this approach, E matrix exponential, which is Laplace inverse of Si minus A inverse. That's right. So we have another approach that we name it Sylvester's interpolation method for matrix exponential E80. What is that? It says that you can calculate matrix exponential through this determinant: 1 lambda 1 lambda 1 2 lambda 1 m minus 1 e lambda 1 t, 1 lambda 2 square lambda 2 m minus 1 e lambda 2 t, and continues 1 lambda m, lambda m square, lambda m power of m minus 1, e lambda m t, and finally I, identity matrix, A matrix, A square, A power of m minus 1, these are matrices. Matrices A, T is 0. You can find the matrix exponential through this. Understand? And now let us do that together. So, but before that, you have to know what are the lambdas. Can you guess that? These lambdas? Yes, lambdas are eigenvalues of matrix A. Okay, so let me do by an example, Let me do it by an example. Okay. How to do it? Say example. Say matrix A for x that is equal to ax plus bu is 1, 0, 0, 2. First that you have to find the eigenvalues. I told you that eigenvalues can be found from lambda I minus a is 0. This is a determinant of lambda minus 1, 0, 0, lambda minus 2. And there's no need to, you know that if you have the diagonal matrix, you can easily find lambda 1 is 1 and the lambda 2 is 2. Obviously it is. Right? This is the rule of the dealing with matrices. So now having that, we have to make that Sylvester determinant. That's right. You have 1, lambda 1. So, but you see, you have to say is e lambda 1 t. 1 lambda 2 e lambda 2 t. That's right. And the last, because here is 2 by 2 matrix, right? This is 2 by 2 matrix. The last column is this. And the last line here gonna be I, A, and again a lambda 80. This is how we divide. That's right. Huh? There's 1 lambda 1, 1 lambda 2, 2 by 2. That's right. Last column is exponentials, lambda 1t, lambda 2t, e80, ia. That's right. So on the other hand, we are writing like this. 1 lambda 1 is 1, e lambda 1 is t, 1, 2, e 2t, lambda 2, and I, a, and lambda, and matrix exponential is 0. I forgot to put it on. It is 0. Understand? So now you have to calculate the determinant. Determinant of this is determinant of this, but determinant of this. 2 cofactors, right? A, E, 80 minus 1. This by determinant of this E 2t, I, E 80, and plus ET gonna be 1, 2, I, and A is equal to 0. Right? Let me double check. Right? Now you have to calculate all of them. So 2E80 minus AE2t minus E80 minus IE2t plus E plus ET in A minus 2I is 0. Now look at here, guys. We want to find this. That's right, a matrix exponential. So this with this gonna be, hold on, this with this gonna be, I'm gonna change the color. This with this gonna be E80, that's right. This with this, right, this with this gonna be and here must be plus. So this is minus, and minus minus plus. So gonna be minus 2t, this with this. Gonna be a minus I, right? And now plus et a minus 2I is 0. Understand? So, on the other hand, E80 that we want to find is E2t a minus I. This is your a minus I. 1, 0, 0, 2 minus I, identity matrix. How much it is? 0, 0, 0, 1, obviously. So this is gonna be 0, 0, 0, 1 minus the screwdriver at E80, and now a minus 2I, a minus 2I multiplying by 2, gonna be minus 1, 0, 0, 0. Here we go. Minus 1, 0, 0, 0. Right? Right? So this is your multiplying, then subtracting. So this is what you get. This is what you get. Let me double check everything. What you get is minus E, sorry, minus, and this minus, sorry, plus ET, plus ET, that's right, because this is minus 1 is plus ET, and 0, and 0, and E2T. Here we go. Understand? So you calculate that. So how we are doing again? So this is a matrix. We are finding the eigenvalues, putting here 1, 1, 1, 2, this and this matrix. Then finding the segment of this matrix. So, and 1C, I'm double checking with you, and 1, 2, IA. Then it's gonna be 2 minus this. It's gonna be minus, and minus minus plus IE2T. That's right. And this is gonna be ET minus 2I. That's right. So this with this goes to E80, and this with this gonna be taking out the minus, gonna be A minus A, right? And plus ET gonna be A, that's right, A minus 2A, that's right, is 0, that's right. So E80 that we want to find, moving to the other side of the equation, gonna be E2T, and minus and minus et in this is right. So this is 0, 0, 0, this, and appears here. And here in minus and minus plus, so plus et. So this is your matrix exponential. So let me go to the MATLAB. Okay, I'm going to do MATLAB by the next week. So I just want to, before leaving, I want to double check that the solution of, where is the pen? Solution of this has no typo or mistake. This solution here, right here. So for that, let me do it with you this time. So, and I want to do by you, and you make sure that everything is correct. Where is that? Okay, we got it. Okay, so first we have to calculate this integration. Okay, how to do that? Look at here, guys. I want to do by you. The first line, the first row. Gonna be integration of 0 to t, to t minus tau, right? E t minus tau in dt. This can be written as integration of 2t from 0 to t e t minus tau in dt minus integration of 0 to t tau e t minus tau dt. This is very trivial, right? So this you have to do by part integration, this part. Okay, so integration of 0 to t tau e t minus tau dt. I'm saying that t is u, and the e t minus tau d tau, this is tau. Oh, these are taus, guys. These are taus. I'm getting older. Is dv. So d tau is du, and from here v is minus e t minus tau. This is a trivial math, that's right. Because you got dv minus plus. So the result gonna be uv gonna be minus tau e t minus tau, that's right, and minus v du, minus and minus plus in du is going to be 0 to tau e t minus tau d tau, right? Clear? So, and obviously the integration of this is minus tau e t minus tau from where? From 0 to t. And integration of this is minus e t minus tau from 0 to t. So what you get is e t minus tau in minus e t minus tau at 1 plus tau from 0 to t. Sorry. So this is for this part only, for this part. So if you put t, it's going to be minus e0, 1 plus t, minus plus et, and this is 1. Sorry. So what you're going to get as et minus, and here I forgot to put 2. So t and minus 1 plus t. That's right. E to the power of t minus 1 plus 2. Now, from here, the integration of this part is t minus e t minus tau from 0 to t. It's gonna be minus t e0 plus minus and minus plus and t et. So this is gonna be t et minus t. That's right. Huh? Clear? Huh? So now you have to do that. So it's gonna be 2t et minus 1, just multiplied by 2, minus 2 et 1 plus t. Right? Huh? So the result is 2t et minus 2 et, and this is minus 2t and minus 2t and minus 2t minus 4t, and the result is this, guys. So the result is et 2t plus 1 minus 4t, if I don't make mistake. So I have to revise it here, guys, because I was curious. This is what is that? So e t plus 1, this 2 is here, not here. This is 4t. That's right. So now let me double check to make sure, because I'm doing with you. So tau is u, this is t not dt. Control needs patience, guys. So it's gonna be minus t minus tau. So this is gonna be uv minus and minus plus v du. This is gonna be this. This is gonna be minus t from t tau. It's gonna be e1 plus tau. So it's gonna be minus e0 1 plus t minus and minus plus et. It's gonna be et minus 1 plus t. So, and this now minus t integration of this minus t n0 tau minus t t0 minus a plus t e tau. So et tau minus t. So multiplied by 2, gonna be 2t e tau. 2 comes out, minus 1, minus this multiplied by 2. Oops, I made a mistake here. Yep, guys, see? Always double checking, guys, always. Here is, so I doubled by this. Now minus 2 EAT minus 2 1 plus t. I see that. So it's gonna be e to e to e t right? And t minus 1, right? Minus 2t, minus 4t, and minus 2. Minus 2t. Minus 4 plus 2. This is the result. Here. T minus 1. T minus 1 minus 2t. So the result is this finally. Result is 2e2 t minus 1 in minus 4t minus 2t minus 4t minus 2. That's the result. Okay. Minus 2. So calculate everything. So see you next class.